Rotem Oshman. Rotem is a faculty member at Tel Aviv University, and she did her PhD at MIT, a postdoc at U of T, where I heard today morning that she sat in Mark's old office while she was here. And then when that was not enough, she went into a postdoc with Mark in Princeton. And she's an expert in communication complexity and distributed computing. And I'll let Rotem talk about some recent results.
Thank you. So this talk is going to continue in the tradition of having Mark listen to his own work, because this is going to be about joint work with Mark, and also with my PhD student, Tal Roth. And I'm going to, so I tried very hard to prepare this talk so that it requires no prior knowledge except probability. Let me know if I missed the mark. There's not that many of us here, so we can ask questions and interact so that everything is clear. So the talk is going to be about communication complexity, and it's going to be a little different from the previous talks that we've seen that had communication complexity in them, including the talk right before mine by O, because here the question is going to be about communication complexity, not as a tool for proving other lower bounds, but as an object of independent interest. So what is communication complexity? My particular interest is in the communication complexity for multiple parties. So in this setup, we're going to have k parties, and each one of them is going to have its own input, xi. And this is going to be in a model called number in hand inputs, which means that every player can see their own input and it cannot see anybody else's input. And that's to distinguish from another model that many people like to think about, which is number on foreheads communication complexity. In that model, the input of player I, we think of it as though it's written on their forehead, so they cannot see it, but everybody else can see it. That model is very different, much harder to prove lower bounds. Number in hand is fairly manageable, and we're going to see why. Can I get this to move? No. Okay. So the goal in general is we would like to compute some joint function of our inputs, and the question is going to be, how many bits do the players need to exchange in order to compute the function that we're interested in? And there are two accepted models for multi-party communication complexity. The first one is called the coordinator model, and this model kind of captures peer-to-peer or unicast communication. There is one coordinator, and these are my k parties. They cannot talk directly to each other. They can only talk to the coordinator, and the coordinator can talk to them. In terms of communication, this is roughly the same as though they could talk directly to each other, because if this party wants to send a message to this party, it can just send it up to the coordinator and have the coordinator forward the message. So it's not a big deal. But it turns out this is much, much easier to analyze technically. So we like to work with this model. And the alternative is, instead of communication by unicast, we can think about communication by broadcast. And this is called the shared blackboard model. Here we imagine that there is a shared blackboard that all the parties can see, and they communicate by writing a message on the board. So you write it one time, and then everybody can see it. Unlike this model, where if I want to communicate with everybody, I'm going to have to separately send messages to everybody and pay for that again and again. So these are the two models. The problem that I'm going to be talking about is the queen of communication complexity, set disjointness. We already saw the two-party version in Ol's talk. This is the k-party version. So we have k sets, x1 through xk. And the goal is to determine if there's a global intersection for all of these sets or not. And we'll also talk a little bit about the generalization of this, which is, instead of just telling me whether or not there is an intersection, find the intersection and output it. This is the more useful version of the problem. So why do we care about set disjointness? We've already seen a hint in the previous talk, but in general, if you understand set disjointness, you also understand a lot of other problems. For example, here is a graph problem to which set disjointness reduces, so lower bounds carry over. Let's say that the inputs of my parties are edge sets from some graph. So I have a very large graph. It's too large to store on one server. So instead, I'm going to partition the edges of this graph between K servers, and I would like them to check if the graph is connected or not. A lower bound on set disjointness implies a lower bound on this problem as well. Different realm of problem is just statistical queries like the number of distinct elements, as we have just seen, and also higher order frequency moments. And there's many, many more where these came from. For some reason, set disjointness just seems to capture what is hard about a lot of different problems. There are also problems that are not exactly set disjointness, but they are very similar in spirit to either disjointness or finding an intersection. For example, if you care about databases, one operation is the join of two or more tables in your database. Join is about finding common values across a column that appears in multiple tables. That is essentially taking an intersection. And even problems that don't look like intersection or disjointness at first glance actually have something like that inherent in them. So here's something completely different. Welfare maximizing allocation. So here we have K buyers and we have N goods. And each buyer is only interested in a subset of the goods, not anything that you give them they're actually going to want. They're only interested in a subset. And the goal is to assign the goods to the buyers so that every buyer is going to get only one good. It's a unit allocation. And I would like to maximize the welfare. So I'd like to assign as many items as possible and make everybody as happy as possible. Turns out that the hard thing about this problem is finding out those rare elements that only a small number of people want, so that I can then give these elements to those people. And that is like intersection. I'm trying to figure out which elements are not in demand, which ones are not in the intersection of the demand sets of the parties. So it turns out, and this is also joint work with Mark, that by proving lower bounds on disjointness, you can also understand this problem. And here's a problem from a completely different domain, which is like my daily job, distributed computing. If you have a network and you want to compute the spanning tree of a network, that is also, there is an intersection problem hidden here, because you might have many possible connections that you can form, and somehow you need to choose only one connection in such a way that all the nodes get connected to the tree. So if some nodes can choose multiple connection points, they still somehow need to choose one. There is an intersection problem hidden here. Okay, so what do we know? Oh, question? Yeah. This is a unit demand problem. I only need to choose one person that wants this item, and I can then give them this item. But think of it as like, if there is an item that a lot of people want, I can essentially assign it at random. That's going to do pretty well for me. So out of all the people that want the item, everybody just says with some probability, I want this item. I'm probably going to find one person that wants it. So those items are easy. About what? There's no value to item. Yeah, they're all equally valuable. Okay, I forgot. It's impossible to go back with this clicker. So set disjointness is very well understood at this point. The two-party communication complexity has been characterized from every perspective that you can possibly imagine at this point, starting from the very famous lower bound of Kalyana Sundaram and Schnitger, and then Razborov, who proved that you cannot beat the naive protocol where Alice takes her n-bit input representation and just sends it over to Bob, and Bob checks if the two sets intersect or not. And this is tight, asymptotically speaking. And this lower bound is distributional, at least Razborov's lower bound. He actually presented an input distribution which requires n bits of communication, or omega n on average. And for the multi-party case, this is actually what I did in my postdoc with Mark. So we characterized both models, and for the coordinator model, again, you cannot beat the trivial protocol where each of my k players takes the characteristic vector of their input set and sends it to the coordinator. And then the coordinator computes the answer. That's going to be kn bits of communication, and that is optimal. But in the shared blackboard model, there is a simple protocol that beats this trivial one. So you can actually do it in roughly linear. You only pay a logarithmic factor in the number of players. And this plus k is just always going to be there because every player has to speak up at least one time. Otherwise, I'm probably not going to be solving the problem correctly. And these bounds are information complexity lower bounds. As Ol mentioned towards the end of his talk, traditionally information complexity lower bounds are worst case lower bounds. They do not yield an actual hard distribution, although in many cases you can then massage them to get the hard distribution out of it. But in these cases we didn't. So these were just worst case lower bounds. Okay, so are we done with set disjointness? My answer is always going to be no. There's always interesting things that are open about set disjointness. And this work actually goes back to what we knew before we knew the answer for two-party set disjointness. So one of the first papers to talk about set disjointness is a paper by Babai, Frankel, and Simon from '86, where they gave a lower bound which was not tight. It was only square root n, and we know that the real answer is n. But their lower bound is actually tight for the case where the two inputs are independent of one another. And they also proved it. They gave a protocol so that for any input distribution on x and y, where x is independent of y, you can solve it in roughly square root n bits up to a log factor here, which was later removed. And this was also generalized to cases where x and y do have some amount of dependence. So this is the mutual information between the inputs. I'm going to be talking about this a lot. So if you don't know what this means, good. If you do know what it means, okay. But just think of it as amount of dependence between the two inputs. And you can see that this interpolates between the completely independent case, where this is just going to be 0, and then we get the square root n lower bounds. And it can go all the way up to n bits of dependence, in which case you recover the linear lower bound of Razborov. So what is going on here? What is actually the hard distribution of Razborov? Here it is. You choose the two inputs of the players to be two uniform sets of size n/4, but conditioned on having an intersection which is either completely empty or only one element with probability 1/2. So how dependent are these two inputs on one another? They are super dependent on one another, right? Because except for this one place where there could either be or not be an intersection, every other element, if I tell you this element is in X, you know for sure that it's not going to be in Y. And if the sets were just independent sets of size n/4, that definitely wouldn't be true, right? If I told you this set is in X, there would still be a probability of about 1/4 that it's in Y. So this translates to roughly 1 bit of dependence, or constant amount per element. And it sums up to a huge amount of dependence between the inputs. And I want to argue that this distribution is maybe not super realistic for a lot of these problems that I mentioned before. A distribution where the inputs are very tightly dependent on one another translates to inputs that are maybe not so realistic. For instance, going back to this welfare allocation problem, if you translate this kind of hard distribution, what you're going to end up with is one item that is super popular. Everybody wants this item. Almost everyone really, really wants to have this item. And that is the item that could be in the intersection or not with constant probability. And all the other items, take it or leave it. With probability 1/2, I want this item. And with probability 1/2, I do not want this item. Is this the realistic kind of input distribution for auctions, for allocations? Probably not, right? It's fairly unusual to have only one thing that we all care about and everything else is just completely up in the air. And the same also goes for these other problems that I talked about, like graph problems, fairly weird graphs that you're going to get from this distribution and so on. And I am lying here, and I'm going to be continuing to lie throughout this talk a lot. So this is kind of like a disclaimer that what I'm saying is only roughly true. This is not exactly the distribution that you get, but it captures the spirit. Okay, so we wanted to ask what happens when you actually look at distributions that we kind of think of as being realistic. And what does that mean? Well, either the inputs are completely independent of one another, because why should the set of items I want have any dependence on the set of items that somebody else wants, right? So we started with completely independent inputs, and then we wanted to push it and see what if there is some dependence between them. How does the communication complexity grow? So we started with completely independent, and we showed that for k-party disjointness, if the inputs are completely independent, then this is the communication complexity that you get. So remember, for 2 parties, it was square root n. For k parties, it's n to the 1 minus 1 over k. And it actually turns out that it doesn't matter which model I'm thinking of. In both models, this is the right answer up to polylog factors. And we thought this was kind of interesting because what it tells us is that in the coordinator model, where the worst case answer is n times k, this shows that when you have complete independence, as the number of players grows, the problem kind of becomes easier. But in the shared blackboard, it's like the other way around somehow. And in both cases, notice that when k becomes log n, as soon as the number of players is logarithmic in the input size, then this is about linear. Okay, so at that point, it just becomes kind of very easy and the number of players doesn't matter anymore. Yeah. Yes. So the way that this is stated is maybe a little confusing, but the lower bound is for a specific product distribution. The upper bound is for any product distribution. Yeah. Of course, there can be product distributions which are much easier. For example, a deterministic distribution is a product distribution, but it's going to be much easier than this. So the lower bound just shows the existence of one hard product distribution. And the upper bound says any product distribution is definitely not harder than this. And if you want to actually extract the intersection of the sets, you can also do it. Let me not belabor this point too much, but we also got that as well. And one thing we thought was interesting here is that unlike the original 2-party protocol that I mentioned from '86, and also unlike its extension that I mentioned, those protocols required the distribution. They needed to know exactly the distribution of the inputs because they were going to sample from that distribution inside the protocol. Our protocol is actually a lot simpler. I'm going to show you more or less how it works. And one nice feature is you do not need to know exactly the distribution. You do need to know something about it. But actually, we showed that if you get some number of samples from the distribution, a sublinear number of samples, then you can approximate it well enough to run the protocol. And it's still open, and I think that's an interesting question. What's the trade-off here? So obviously, if you know nothing about the distribution, it's easy to see that you cannot do anything non-trivial. It's just as hard as the worst case. And if you fully know the distribution, then this is the bound. What is the trade-off between the effort that you spend learning the distribution and the communication complexity that you can then get when you're working with inputs from that distribution? Okay, so this is for fully independent inputs. What happens when there can be some dependence? So we were able to actually almost tightly characterize this as well. If D measures the dependence in a sense that I'm going to talk about a lot, then this is the bound that you get. It exactly interpolates in the same way that we had for two parties. So this part was here for independent inputs. And now you also get this dependence term. And this is kind of the precise answer. Okay, and as I said, I'm going to be talking a lot. I'm probably spending most of the talk just figuring out what is the right way to measure the dependence between the inputs. And this is only for shared Blackboard. Unlike the previous result, this only works when the players communicate by broadcast, by writing messages on the board. For coordinator, it's still open for reasons that I think are interesting, and I'm going to talk about. And again, we can generalize this to computing the intersection is actually easier than getting this protocol. And then you also get some dependence on the size of the intersection. Okay, so this is a good point for questions if there are any. Yes. This one actually, the way we understand it right now, you do need to know the distribution. It's not hard to see that you don't precisely need to know it, but I can't give you a clean result of the sort that I had for the fully independent case, saying with this number of samples, you can then just go and run your protocol. That's going to work. Here, something more complicated happens, which we don't fully understand yet. Yeah. So this is still open. Okay, so what am I going to do for the remainder of the talk? I'm going to spend a lot of time talking about what it means for more than two random variables to have some dependence between them, and how should we measure this dependence. And to the extent that I still have time after that, I'm going to tell you a little bit about the protocol. And if I still have time after that, then I'm also going to tell you about the lower bound. And again, there's going to be even more lying in the rest of the talk than there has been. So far, I'm going to be glossing over a lot of technical details, trying to convey the high-level ideas. Okay, so let's talk about how to measure dependence between random variables. For two random variables, there is one canonical way to do it, which is mutual information. If you have two random variables, A and B, then we like to draw this fake Venn diagram where we think about the uncertainty that we have about A, the entropy of A, and the uncertainty that we have about B. And somehow the mutual information between them should be this part, the part that I'm uncertain about, but it's somehow the same for A and B, so that if you know A, this part of B is revealed to you, and vice versa. So there are many formulas for capturing this, which are equivalent. For example, I can write this as the entropy of A, the uncertainty of A, minus this part here, which is the uncertainty that remains in A after the value of B is revealed. This is the conditional entropy of A after I show you the value of B. And this is one way to define mutual information. And this is symmetric, so I could also have written it the other way around. It's my uncertainty about B minus whatever uncertainty remains after seeing A. Here is another way to capture this. I can write it as the joint uncertainty of A and B together, which is like the area of this whole diagram, minus this part here, which is the conditional uncertainty of A given B, and then minus this part here, which is the conditional uncertainty of B given A. Sorry, this is confusing, right? If you subtract out these two parts, then again, you're going to just be left with the mutual information. And yet another way, you can write this as the uncertainty about A plus the uncertainty about B. So now I'm double counting, but the amount by which I'm double counting is exactly this. So then subtract out the joint entropy, and you're left exactly with this. All these formulas are exactly equivalent to one another. A nice thing that I cannot draw in any way is that mutual information also captures a more operational kind of thing about these random variables and their distribution, which is it's exactly the difference measured in something called KL divergence between the joint distribution of these variables and the product distribution, where I sample A from its marginal distribution, and I independently go and sample B without looking at A. So the amount by which these two experiments differ, this is also the amount of dependence between A and B. All right, how do we generalize to more than two random variables? Well, you can pick any of these definitions and you can go and generalize it and hope that some miracle will happen and everything will turn out to be exactly the same, the way that it did with two. But the miracle doesn't happen. And these generalizations are not the same for more than two random variables, which is one of the things that I found the most interesting actually in this work. So here's one way to generalize. We start from this, this definition, which was the uncertainty of A plus that of B minus the joint uncertainty. If you generalize this to more than two, you are going to get the sum of the individual uncertainties minus the joint uncertainty of everything together. And this is definitely a legit way to generalize, and it has a name. It's called the total correlation between all these variables. In terms of a picture, this is what we are doing here, right? We are summing these uncertainties, which double counts things by different amounts, right? This is overcounted one time, and this is overcounted two times. So then I'm going to subtract out like the whole area of this thing, but I'm still counting this more than I am counting this and this and this. So this is one way, total correlation. Very nice property of total correlation. It does have this interpretation that it's equal to the difference between sampling these variables jointly versus sampling them independently from their marginals. So most people, when they think of dependence between multiple variables, they think of total correlation. And that is also what we thought of. And we were very sure that it's the right way to generalize until I sat in Mark's office for a few hours and whined to him about the fact that we can't get the protocol to work. And then Mark said, well, maybe that's not the right way. Maybe we should measure dependence in a different way. And this is the different way. So let's try to generalize a different notion of mutual information, this notion. And this is what we're now going to get. So this is called dual total correlation, although Mark didn't know this, I believe, when he invented it again. This is the joint entropy of everything. And now I'm going to subtract out what remains unknown about each variable when I show you the other ones. And in terms of a picture, this is what we're doing here. We're starting with the joint uncertainty, which is this whole area. And now we're going to subtract out each of these. So this is what I don't know about A, when you can see everything else, right? And the same here for B and for C. And the area that is left is this dual total correlation. But you can see that the overcounting is different here. This middle intersection is not counted more times than these pairwise intersections. Yeah.
If you took the previous definition and did kind of inclusion exclusion, then wouldn't you get something similar?
What do you mean by did inclusion exclusion?
Like, so you count everything, you subtract the pairs, you add the 3 times.
Yes.
And you're not,
Yes.
then you would get.
Yeah, you can definitely get this definition in more than one way, but you get a different value. These are not the same definition. I'm going to show an example in a second that you can get different values actually. And these things have different interpretations. For example, this really nice property that we have. Oh no, this only goes forward. This property. This is true for total correlation. It's not true for dual total correlation.
Yeah, but my point, if you took this definition and changed it.
Yes.
Like I would define it different. My intuition would be to define differently. H of A plus H of B plus H of C minus H of AB minus H of BC minus plus the.
You can.
And then won't you get what you got before, like in the other?
I think you would, yes. But these are,
Yeah, but these are different.
they're different, yeah. So the point I'm trying to make here is that these things which miraculously coincide for 2 random variables do not coincide anymore when you have more than 2 random variables. And now you have different definitions. And let me show you simple examples that demonstrate the difference. So here's one such example. Let's say I sample a variable, which is just a fair coin, Bernoulli 1/2. And then all the other variables are equal to this variable. So what do we get in terms of dependence for these 2 definitions? For the total correlation, I have here joint entropy of, sorry, not joint entropy. So each one of the variables by itself only has 1 bit of entropy, right? So this is k times that. And what is their joint entropy? Still only 1 bit. There's truly only 1 bit happening here. So this is going to be k minus 1. Well, what do we get for the other definition? So now this we said is 1. But how much uncertainty do I have about any of these variables when you can see all the other ones? Nothing, right? So you only have 1 bit of dependence here. And to me, this is capturing this lack of overcounting, right? There is 1 bit of dependence, but it's the same bit of dependence between all the variables, right? So this counts it again and again and again. This depends on this and on this and on this and on this. This somehow counts it only 1 time. And here's an example that goes the other way. Let's say that my k bits now are independent, but subject to having an XOR of 0. So now they have pretty high joint entropy, right? Almost full joint entropy, which is going to be k minus 1 here. Individually, they have full entropy, 1 bit. So I'm going to get 1 bit of dependence here between all of them. For the other definition, it's actually going to work the other way around, because we said the joint entropy of everything together is k minus 1. But again, when I reveal to you all the variables except 1, you know the value of the last one. So no uncertainty remains. So this is 0. All right. So this example is also kind of educational, in my opinion, right? Because you have this dependence here, but it's smeared across all the variables in a way that is not easy to disentangle. And so the total correlation between them is very high. It captures somehow the fact that this is like a big dependence. But in terms of dual total, sorry, other way around, this is not easy to disentangle. So this is the definition. I even confuse myself. But somehow here, the dual total correlation is saying like, it just show you 1 bit and I've shown you like the whole dependence. I just need to show you the XOR. So which one is the right way? At least for the purpose of multi-party set disjointness. So the answer is we still don't know. Our upper bound is analyzed in terms of dual total correlation. But our lower bound is analyzed in terms of total correlation. Fortunately, right now, that's not a big issue, because remember that I said when the number of players goes to log n, everything kind of becomes trivial, and the lower bound is linear, and kind of that's what we're aiming for. Well, these two quantities can only differ by k-1 multiplicative factor. So this is just going to translate to a logarithmic factor in our lower bound. But am I happy about this state of affairs? No. I would like to know what is the true answer. Okay, so are there any questions up to here? All right, so I'll try to hint at why these are kind of the natural things to use for the protocol and for the lower bound. For the protocol, dual total correlation seems to capture how many players or how much effort you need to expend to break the dependence, to kind of disentangle things. And this you can see from this example that we had where everything is equal to 1 bit. In this case, if one player speaks and tells you the bit, you have broken the dependence. Why should I charge k-1 for this kind of dependence when by just expending 1 bit of communication or information, I can break this dependence? And for the other example, we had this kind of wide dependence. In order to break this dependence, I need to expend a lot of communication or information. I cannot break this dependence until all the players have spoken except the last one. So this, I should charge a high amount, but total correlation doesn't. So this seems to be more natural for the communication protocol. For the lower bound, it's a little bit harder to give the intuition of why total correlation and not dual total correlation, but this really goes back to this characterization of what would be the difference between just sampling jointly versus sampling independently from the marginals. Our lower bound is just stated in terms of this, the hard distribution that we presented. It has very low total correlation. It has very high dual total correlation. So this is still somewhat open. Okay, let me tell you a little bit about how the protocol works. And I'm going to be really kind of hand-waving a lot of it, but at least I can explain how the product case works and hint at how you can push it to incorporate dependence. I feel like I always need to put up this disclaimer, which is, all right, so here's the high-level structure of the protocol for set disjointness. I'm going to iterate over the elements just 1 through n. And each one of them, I'm just going to check if it's in the intersection or not. That's the part that has to be very efficient because I'm going to be doing it for each and every element. And then if I have found an element in the intersection, I'm going to say it's not empty. And if I haven't, I'm going to say it's empty. For intersection, I'm going to do the same thing, but I'm not going to stop when I find an intersection. And something that I'm not going to kind of emphasize a lot here, going over these elements, actually, you have to be careful how you do it. If you do it using communication, so you devise a communication protocol for each element, and then you go and do them one after the other, it won't be efficient. What you actually need to do is analyze the single element information cost and then go and squeeze everything by compressing it to an efficient communication protocol. So how do you solve one element? There's this one element. I would like to figure out if this element is in the intersection of everybody's input, yes or no. And let me denote by pi the probability of this element being in the intersection. And let me pretend for now that the inputs are independent. If the inputs were independent, then the probability of having this element in everybody's input, it would just be the product of the individual probabilities of having it in each player's input. And this would actually be really nice because it would mean that the probability that some player has this, right? For some player, the one with the smallest probability of having it, the probability that they have it is pretty small. It's only the probability that everybody has it to the power 1 over k. So how can I figure out if this element is in the intersection or not? I'm going to choose this player, the one that has the least probability of having the element in their input. And this player is now kind of in charge of this element. They're going to, first of all, announce, did I get this element, yes or no? And remember, this is supposed to not happen very frequently. So most of the time, they're going to say, I don't have this element. And then we don't need to do anything more. It's not in the intersection. Some probability of the time, unfortunately, they will have the element in their input. And then we're just going to do the most naive thing. Everybody else will follow suit and say if they have the element or not. So what's the cost of this simple one element protocol? With probability pi to the 1 over k at most, we have to do this. And then everybody has to speak. Okay, so in total, this is the expected cost of this protocol. Yeah. Sorry? Yes, okay. So this is going back to what I know about the distribution. This player has to be fixed in advance. For every element, I need to know in advance who is in charge of this element. If you know the distribution in full, then you know. But you don't need to know the distribution, right? It's enough to know the marginal probability for each player of having this element. And that's why I said that you only need some rough knowledge about this distribution. For example, I don't care at all in this protocol about dependencies between different elements in the input. And it's much, much easier to estimate this marginal probability compared to the distribution of a full input of one player. That would require exponentially many samples. This requires polynomially many samples, right? I still don't know if that's inherent, but I believe that it is. Okay, so this is the kind of bare bones of the protocol. And then what do? You're going to do this potentially many times because you have to solve all of the elements. So this is going to be the cost. For each element, I pay k times the probability that I had to say stuff about this element. And then using Holder, you can show that this is the bound that you get. And this thing here is not working. This is just the expected size of the intersection, right? So that is what we were aiming for in order to compute the intersection. If you want to solve disjointness, you do the same thing, but you stop as soon as you find one intersection. And then by a kind of cute analysis trick, you can show that you don't get this. Doesn't matter. Any order, it's perfectly fine. Even for disjointness, and the trick there is the higher the probability of having an element, the more I pay for it, but also there's higher probability I'm going to stop, right? So it's kind of like a balancing act. Okay, so this is the protocol that we would have had if everything was independent. What if it's not? What if things are not independent? So what's going to break here? This assumption that the probability of having an input in the intersection is the product of the individual probabilities of having it in each player's input. So that's not true anymore, which means I'm no longer guaranteed to have a player whose probability of having this input is not that big. Okay, so what do you need to do? You need to massage this in a way that incorporates the dependence between the inputs. Because remember, dependence is somehow like how different would it be if I sampled one player independently of everybody else versus if I sampled everything together jointly. So what we're able to show is that there is a way to still choose this kind of low probability player, except now the probability that they have this in their input, you also get a penalty term, which is how dependent is this player's input on everybody else's input in this particular element, in this coordinate. And that means this is kind of why this becomes more complicated. So now I need to know dependencies as well as just marginal expectations, right? And this is why I don't have a clean formulation of what exactly I need to know about the distribution to implement this protocol. And another thing I'm not talking about in these slides at all, as you go through the protocol here, the distribution changes because I reveal some of the inputs. So you also need to incorporate that here in the dependencies where in the previous protocol you didn't. Okay, so then essentially this is what the protocol becomes. You just choose a player that minimizes this. And that player does what we said before, announces if they have the element or not. If they don't, we just move on. If they do, everybody sells their input. And then we can somehow analyze the cost by charging it against the probability that this is in the intersection, plus the dependence between the inputs of the players. And that's quite tricky to actually do, but I'm not going to say anything more about it. Okay, let me give you 2 bits of information about the lower bound. So this is going to be super, super vague. First of all, what is a hard distribution? I'm just going to be talking about the fully independent case here. If you want a hard distribution for determining whether or not the intersection is empty, the intuition of Razborov's hard distribution is still good. The intersection should be either fully empty or really, really small, right? That's what we want. If the intersection is big, it becomes easy to find something in it. So that is not going to be a hard distribution. And if you now demand independence between the inputs, there's only one reasonable way to achieve that, which is to say, let me just have a distribution where every element is in every input with this probability. And this exactly balances things so that each element is in the intersection with probability 1 over n, right? And then the expected intersection size is constant. And also with constant probability, I am going to get an empty intersection. So this is the hard distribution, super natural, I think. And you get really natural graphs from this distribution as well. Just everything is really clean and simple. Yeah. Which property? This property. Yes, right. It doesn't necessarily mean that's what you would have to use for a lower bound, right? But it is suggestive that you would want as much uncertainty about the inputs as you can. Yeah, that's right. But maybe there is, I can find examples where that's not actually the hard distribution. So you want a lot of entropy, but not necessarily maximum entropy distribution. Okay, so what is the goal of a communication protocol? And in general, how do you prove information complexity lower bounds? You think of it this way. When the protocol is just starting out, some inputs, the protocol is supposed to say yes, and some inputs, the protocol is supposed to say no. They should be roughly mixed so that it's not kind of easy to just guess always no, and then the answer is correct with high probability. This is when I haven't executed the protocol yet. After I execute the protocol, things should look very different. If the protocol generated a transcript where it said the answer is disjoint, conditioned on that transcript, which inputs should be likely? These ones. the ones where it really is disjoint, right? Because every input that is still likely when the protocol says disjoint, but this input is not disjoint, it directly contributes to the error of the protocol. And the same is true for when the protocol says non-disjoint, it should look roughly like this. So we should be thinking of the task of a protocol as changing the posterior distribution, right? And then the question is, what is the cost of shifting the prior distribution to the posterior distribution so that you can achieve this? And how do you do that? You can basically expend your effort in two different ways. You can expend your effort, I'm just going to be skipping this because it is boring. You can expend your effort to shift one coordinate. So for example, if I have a prior probability of 1/2 for this bit to be 1, the protocol can spend some communication to shift the prior by announcing that it is 1. And then the posterior probability becomes 1. Now I know for sure it is 1, right? This is one way you focus your attention on one coordinate, you just shift the probability of that coordinate. A different thing that you can do is to spend effort on creating dependencies between different coordinates. For example, if I have this prior probability for 2 bits, right, they're uniformly random and independent, I can spend some communication to create dependence between them by announcing that one of them is 1 if and only if the other one is 1 as well. So the XOR of these 2 bits. This is still 1 bit of communication. And now the posterior distribution, it looks like this, right? They became fully dependent. But I still don't know either of them. I didn't do this. I did something different. Okay, so these are essentially the ways that we want to think of the information budget that the protocol has. It's always doing either this or this. Every time it wants to do one of these things, it has to take out its credit card and pay in terms of information. It has to spend information to accomplish this. And this is how the protocol works. So I'm going to essentially stop at this point. We are going to just describe at a super high level the way the protocol works. This is the total budget that I give the protocol. It can spend this budget on the coordinates in any way that it wants, but since I have n coordinates, a typical coordinate is impacted only this much. That means that a typical coordinate, first of all, you were only able to shift its marginal distribution by roughly this much. And also you were able to create dependencies between this coordinate and other stuff also by this much. So zooming in just on this part, let's say I'm only doing this. The coordinates remain independent after the protocol runs. That is an essential property of communication protocols. If I had prior probability 1 over n to the 1 over k that this is in my input, and let's say I shifted it by this over 100, I still have almost the same posterior probability as my prior, which means I can now take the product across all players. I'm still going to have this in the intersection with roughly the same prior probability that I had initially. Okay, and this kind of lets you analyze each coordinate independently and then adds everything up. All right, so I'm going to skip directly to the end from here. So just to conclude, we've analyzed the general distribution hardness of disjointness under distributions that have some amount of dependence between them. We were able to do this for the shared blackboard. The reason our answer is nearly tight is that we were able to avoid a hard question, which is what is the right way to measure dependence here? It turns out, if the number of players is small, it doesn't matter that much. For the shared blackboard, that's enough. For the coordinator model, that's not enough. You have a lot of players. We know that the communication in the worst case blows up linearly with the number of players. So to solve that, we're going to have to figure out what is the right way to measure dependence. And I think that is kind of a a really interesting open problem here. The other problems that came out of this more as like a side question, a side quest in some sense, are these questions that I discussed of like, do you really need to know the distribution? What do you need to know about the distribution? Are there questions related to, for example, learning a distribution in some sense of regret minimization or total effort that I spent, and so on? So these are questions that I think remain really interesting. This is another question I'll just mention it maybe because I do think it's interesting. Okay, so a lot of things that we know for two parties, we don't know for multiple parties. A lot of things that we know for one-way communication, we don't know for interactive communication. And this is one of them. So we know that for one-way communication, which is just compression, if you don't know exactly the right distribution, if you don't exactly know the prior distribution, this will be your penalty that you're going to pay. Your compression will be less efficient than it could have been by this much. For interactive communication, we don't know. We don't have such an understanding. And that's just an open question I wanted to float out here. All right, so now let me finally conclude and let us go to lunch.